So let me start off by saying, please ask lots of questions. In particular, I find it a little bit awkward having talks where the communication is solely one directional. So I like feedback, I sort of rely on feedback, and if nobody asks questions, it'll make me very sad. So please don't do that to me. So what I'm going to be talking about today, this one will go up too, right? Okay, good. So what I'll be talking about today is the sphere packing problem in Rn. We're going to have a bunch of identical congruent balls. We want to stick them into Euclidean space without overlap. They can be tangent, but their interiors have to be disjoint. And we want to stick them in as densely as possible so they cover as much of space as we can. So this is a pretty familiar problem in low dimensions. And when n is less than or equal to 3, this is known. In one dimension, it's trivial. The interval packing problem on the line, you can cover the entire line completely. In 2 dimensions, it's not that hard, but it takes some work to prove it rigorously. And in 3 dimensions, this is the famous Kepler conjecture. It's obvious what the answer is. It's the way you see, oranges stacked in the grocery store. But it's not at all obvious how to prove it. And Hales gave a horrifically complicated proof about 15 years ago. Exactly, yeah. It involved elaborate human arguments and huge computer calculations. And I'm hoping that sometime this year he completes the first completely formally verified proof of this using a computer proof checker. We'll see. In any case, in up to 3 dimensions we know the answer. In 4 or more dimensions, there's no case where we know the answer exactly. So normally, my main interest in this problem is what happens, yes? Mm-hmm.
Why does Microsoft
Yep. Okay, so 2 reasons. One reason is just because Microsoft is one reason is Microsoft's interested in fundamental research, regardless of whether it's directly applicable to Microsoft products. A second reason is this turns out to be much more applicable than it sounds. And this is what Shannon realized in 1948, that up until that point, if you said, oh, I'm going to do sphere packing in 1,000 dimensions, it would sound ridiculous. And what Shannon realized, though, is that this is basically communication over a noisy but continuous communication channel. So for a sort of toy version of this, imagine that you're sending, radio signals, and you're measuring the signal strength at 1,000 different frequencies. So you're basically receiving a 1,000-dimensional vector. So the problem is there's going to be some noise. So what you transmit isn't exactly what gets received. You want to agree on some sort of error-correcting code in advance, where you select a bunch of signals that are well separated from each other so they aren't likely to get confused, but where subject to that, you're packing them in as densely as possible. And so this is highly relevant for things like cell phones. So it turns out that for practical purposes, maybe 3 dimensions is the most practical, but 1,000 dimensions is about as practical as 3. Okay, so normally what I'm most interested in is sort of remarkable cases. So for example, 8 or 24 dimensions where amazing lattices have great properties. But what I'm going to talk about today is the asymptotic limit. What happens as n goes to infinity?
So physics don't,
Yep.
but other conjectures, conjectures for other values of n?
There are for certain values of n. For 4, 5, 6, 7, 8 dimensions, there are reliable conjectures. For certain higher dimensions, maybe 12, 16, 24, there are. And we've got some okay guesses in between there. But if you pick, say, 53 dimensions, nobody has any plausible candidate for what the best packing is in that dimension.
And those dimensions that you mentioned, those are all lattice packings?
Yes and no. The thing is, the ones I mentioned were all lattice packings. There are some good non-lattice packings, for example, in 10 dimensions that are better than any known lattice. What seems to happen is that non-lattice packings probably do better and better as the dimension goes up, and lattices probably never win asymptotically, but nobody has a clue how to prove that. Other questions?
24 is quite long.
Yes, so 8 and 24 dimensions, I really believe you ought to solve this, but that's a topic for another talk. Okay, so let's look at the maximum density that you can achieve in n dimensions. You have to be a little bit careful when defining what you mean by the maximum density. The problem is if you just take an arbitrary packing, it won't necessarily have a well-defined density. And it's not too hard to make this rigorous. You can take some big region, say a sphere. You can ask how densely can you pack it in this sphere. You can let the radius of the sphere go to infinity. And it's pretty easy to prove that, what happens in the boundary is negligible, and this gives a good notion of Euclidean packing density. So what do we know about this? So modulo sub-exponential factors, we know it's always greater than or equal to 2 to the n, and it's at most about 2 to the minus 0.599n as n goes to infinity. And it's a sad fact for humanity that we can't pin down the density to within better than this ridiculous exponential factor. I mean, aside from the applications in coding theory, this feels like something, it's a simple enough problem humanity ought to know the answer, but we really don't. So the lower bound is basically due to Minkowski. And the upper bound is from a paper by Kabatiansky and Levenstein. In 1978. So what I'll be talking about today is upper bounds for this. But let me tell you a proof of density 2 to the minus n just for completeness. Because it's appalling that we only barely know how to improve this. So one way to prove it is to define what's called a saturated packing, namely one where you can't add any more spheres, without creating overlap, of course. What I claim is every saturated packing has density at least 2 to the minus n. The reason is, imagine you've got a bunch of spheres where you can't add any more. So what you can imagine doing is doubling the radius of all of your spheres. I claim if you double the radius, you'd better cover space completely. If you had anything that wasn't in any of the doubled radius balls, you could put a new sphere of the original radius in there, and it would fit. So if you have a saturated packing, then what that means is if you double the radius, you cover space completely. And when you double the radius, you multiply the volume by 2 to the n. So what that means is you'd better have covered at least a 2 to the minus n fraction before you doubled it. And so Minkowski improved on this density bound by a factor of 2 early in the 20th century. People improved on it by a non-constant factor, by a linear factor at various points in the 20th century. Keith Ball got up to a factor of 2 times n in the 1990s. And just recently, Akshay Venkatesh improved it by an n log n factor in certain dimensions. But still, it's really sad that, I don't know. The thing is, I'm willing to believe that 2 to the minus, the exponential factor may be right, but for example, I can't believe that it's really a log n factor higher in certain dimensions than others. My guess is you might even be able to get a sort of sizable polynomial factor bigger. Yep. The exponent might be right, but really we don't have any evidence. The thing is, I mean, the only evidence we've got is nobody can beat it. Exactly, but the thing is that, so the question here is, where in this range is the actual density? I think most people who have an opinion suspect it's probably 2 to the minus n, but I don't know if there's any good reason for that except that nobody's thought of anything better.
You have a better reason, Peter?
So here, so,
It's very similar to the
yep.
magnetic problem.
Yep. Okay, here's the one counter argument I know. You can do exactly the same thing in the setting of discrete error-correcting codes. That the analog of Minkowski is the so-called Gilbert-Varshamov bound. And it turns out that for error-correcting codes over a big alphabet, you actually can do better via algebraic geometry codes than the randomized constructions like this. So that's one of the rare cases where you can actually beat this. And that's why I haven't entirely given up hope that the 2 to the minus n might simply be wrong, that there are very closely related settings where improvements are possible. It's just not clear whether this is one of them.
But at the lower bound, nobody has anything like explicitly known anywhere near that.
Exactly. So, I mean, you might... Yes, if you take, your favorite lattice, say, the integer lattice Zn, the density of that's terrible. The problem is you've got 1 point per unit volume. On the other hand, the volume of a sphere has a factorial in the denominator, so you don't even get an exponentially large density there. Exponentially large is a weird way to describe something that's exponentially decaying, but it decays super exponentially. And in fact, any sort of simple lattice you can write down is going to have super exponential decay as n goes to infinity. And there are some, more or less constructive versions that give something exponential that's much worse than this. But still, those are fairly elaborate. They're not simple things you can write down, and they're also nowhere near 2 to the minus n. So basically, these sorts of non-constructive arguments are really the best we've got so far.
So would that correspond to the, maybe you don't know the answer.
Yep.
System mechanics, you can ask where the region of analyticity is.
Mm-hmm.
If you guess it is, well, has an estimate on the gasket. Something like that, but I don't know if it matches.
I don't know.
Would you have analyticity up to two gaskets related to that? Let's just random.
Mm-hmm.
Yeah, just hard spheres.
I mean, the hard sphere model, the sort of random hard sphere model is even more subtle than this is. And I mean, we don't even understand that in 3 dimensions, really.
You understand,
Yep.
You understand the high
Mm-hmm.
temperature phase, right?
Yep, exactly. But the problem is that...
The low density phase.
Mm-hmm. Yep. Mm-hmm. But the problem is that I mean, it's not even known, for example, whether there is a phase transition in 3 dimensions. Yep. But the thing is, that's connected to part of why this is so subtle, that, for example, you could ask, is there a phase transition in very high dimensions? And one very plausible scenario is that there might not be, because it might be disordered all the way to the maximum density. We really don't know. Other questions? Yep. You can show, so this argument doesn't do it for lattices. It's actually really hard to make saturated lattices because basically for a lattice you've got an exponential amount of space where holes can appear and only a quadratic number of parameters to control them. So with lattices, probably there are no saturated lattices in high dimensions. However, Minkowski did this for lattices. So in fact, all of the densest known packings in high dimensions are lattices, despite the fact that lattices probably aren't that good. The problem is lattices are a lot more tractable, and something that's not very good that we can analyze beats something that might be better that we can't. But yeah, you're right that this doesn't give lattices, but in fact, lattices are known. Other questions? By the way, philosophically, I probably shouldn't say this on camera, but philosophically I feel like background questions like that are usually more valuable and interesting for the audience than what the speaker actually has to say, so feel free to keep asking them. Okay, so what I want to talk about today is how to prove bounds like this upper bound, because there's an aspect of this that I find sort of distressing. It's one of these cases where you look at an argument and you say, okay, that was a clever argument, Kapitiansky and Levenstein are obviously smart guys, but this can't possibly be the right way to do it. And even though they did it in 1978, we still don't know the right way to do it. But what I'll talk about today is maybe some progress in that direction. So in particular, what I want to talk about is 3 things. A sort of simple variant of the Kapitiansky-Levenstein argument that's slightly better. So I wish slightly better meant improving the exponent, but it doesn't. what slightly better means is better by a constant factor. I won't say this improvement matters for anything, but it at least shows that whatever they were doing wasn't quite sharp, and I hope it might suggest ways to improve it further in the future. So I'll talk about that first. It's actually quite short, and then I'll spend the rest of the time talking about linear programming bounds and how they led, first of all, to Kapitiansky-Levenstein, and secondly, to a different perspective on this proof. And that'll take basically the second half of the talk. And what I'm not going to try to say a lot about today, because there's only so much time in an hour, is hyperbolic space. But let me say very briefly something about this. So a very natural thing to look at, besides Euclidean sphere packing, is hyperbolic sphere packings. So these are actually surprisingly subtle to define. Part of the problem is the exponential volume growth in hyperbolic space. That I sort of waved my hands when we defined the maximum density for Euclidean sphere packing and said, chop space up into a finite region, the boundary doesn't really matter. In hyperbolic space, the boundary really does matter. And if you try to do things naively, the boundary is going to be the dominant term, and it's going to ruin everything you do. So there actually is a beautiful way of getting around. Let me give one example of the sort of pathological things that can happen. So given a packing, you can try to define the density centered at a point. So what you do is you take your base point, you look at bigger and bigger balls centered at that point, and you look at the density within each ball. And so if this limit exists in Euclidean space, then it's independent of the base point. If you tried doing it at another base point, you would get the same limit. And the reason is pretty obvious. If you have two balls centered at fixed points, that sounds awkward because fixed point means something else, but whatever. Two balls centered at specified points of very large radius, they almost entirely overlap, and you're going to get the same density. In hyperbolic space, this is totally false. You can do something like, imagine taking a dense packing, but taking a sort of narrow angle around your base point and emitting it. So we've filled up space over here pretty densely, but we left out a thin wedge. So if we compute the density centered at this base point, for each sphere, we're going to be missing just a sort of thin fraction of it. And so we're going to get most of the density we had there. On the other hand, you can find a point out here and a line where this entire half space is contained in the thin wedge. And now if you try doing density centered here, you're missing at least half the spheres centered at that point. So from this perspective, you're missing a majority of them. From this perspective, you're missing just a tiny fraction. And you simply don't get a consistently defined density. So this bothered people for a long time. And in a beautiful paper about 10 years ago, Lewis Bowen and Charles Radin gave a beautiful definition in terms of ergodic theory. I don't want to go into this in detail. That would also be another talk. But the basic idea is this. Instead of looking at a packing as an isolated object, what they do is they look at measures on the space of all packings. So they look at the space of all packings. You can topologize that by convergence and compact subsets so that you get a nice compact space of packings. So you have a nice compact space of all packings. And what you can do is you can look at isometry invariant probability measures on it. Let's call this space S. So you have a notion of picking a random packing instead of some fixed packing. And in certain cases, for example, if your packing is invariant under a discrete group with finite covolume, then you could easily do an averaging argument to convert it to a measure in this sense. On the other hand, what they show is if you have an invariant probability measure like this, let's say it's ergodic, so you're not combining several of them. If you have an ergodic invariant probability measure, sampling from it with probability 1 gives you an incredibly well-behaved packing, one which completely avoids pathologies like this one, a packing where everything works beautifully. So basically, Bowen and Radin reframed the problem of hyperbolic packings as, can you find an invariant probability measure which has a high density? Where now it's easy to define the density of a probability measure. You say, you pick your favorite point, say the origin. It doesn't matter which because it's isometry invariant. And you say, if I pick a random packing from this measure, what's the probability the origin is going to be in one of those balls? And that's the density. So Bowen and Radin gave a very nice, beautiful definition of hyperbolic packing density, which is arguably the right one. The problem is, hyperbolic density, it's just trickier to say anything about it. And there have been some bounds on this. So for example, also in 1978, Borotsky proved a hyperbolic density bound by a local argument. I can say more specifically what he did. What he did was he said, imagine a regular hyperbolic simplex. And imagine looking at balls centered, that doesn't look like it's centered there, but it is. And look at balls centered at the vertices of your simplex. And look at the fraction of your simplex they cover. And he said, no hyperbolic packing can do better than that density. And he proved this decades before the Bowen and Radin definition, but he did this by a sort of local geometrical argument, which pretty clearly should work for any reasonable definition of density. In fact, it does, and it shows that the Bowen-Radin density has a certain exponentially decreasing upper bound. Basically, it's going to be 2 to the minus n over 2, at least in the worst case. One thing about hyperbolic packing is the hyperbolic packing problem depends on the radius of the balls you're using. The point is that you've got constant curvature -1, and that sets a length scale, so it's no longer scaling invariant. But it's one more parameter to deal with. So one thing that I won't talk about in detail today, but using the techniques that I'll talk about, you can prove the Kabatiansky-Levenstein bound in hyperbolic space also. So at least in this case, we can exponentially improve the upper bound from 2 to the minus 0.5n to almost 2 to the minus 0.6n. So any questions about anything before I start talking about some of the proof techniques? Yes?
So I suppose Radin limit to hyperbolic, right? Same ideas used for.
Probably you could do it for packings in other cases. It depends on some elementary geometry of triangles, actually. And I know how this works in the spherical, Euclidean, and hyperbolic cases because we've got trigonometry there. Any geometry where you could carry over this argument, you could do this in, but I think it would depend on what the sort of geometry, and I haven't explored it. But it's the sort of thing where it's a pretty elementary argument, so in any given case, one could just sit down and figure out whether it works or not. Okay, so what was the basic idea behind what Kabatiansky and Levenstein did? So what they did was they said, well, Euclidean space is big, it's not compact, we don't really understand it very well. Spheres are much simpler. And so they said, let's study the sphere packing problem on the surface of a sphere and then try to reduce the Euclidean case to that. So what they did is they looked at spherical codes. So in other words, what you're going to do is you're going to look at a subset of, let's say, the unit sphere with some minimal angle, say theta, formed with the origin. So what you're going to be doing is putting points on the sphere in such a way that no two of them get too close to each other. An equivalent way of thinking about it is if you use spherical caps of radius theta over 2, you get a packing of spherical caps on the surface of a sphere. So this is just the sphere packing problem. Oh yeah, they didn't introduce this problem, but they used it. Excuse me? Yep. Oh, definitely. And I believe he used spherical codes, but not in the particular way we're about to discuss, as far as I know. Okay. So let's define A of n theta to be the maximum size of such a spherical code. In other words, the greatest number of points you can put on a sphere in n dimensions so that no two of them get closer than angle theta from each other. So what Kaputiansky and Levenstein proved is the following lemma. They said that the sphere packing density in Rn for any theta is bounded by the sine of theta over 2 to the nth power times A of n plus 1 theta. So what this says is if you have a good bound on spherical code sizes, you get a density bound out of this. So on the one hand, this is kind of, it's a little bit sad that we have to pass to spheres to do this. But on the other hand, we know a lot more about spheres than we do about Euclidean space. And so what they did was they took the bounds for spheres. In fact, they proved the best bounds known for spherical codes. And they used this to derive Euclidean bounds. However, they did it in a way I find very strange. So they bounded this. In fact, let me tell you what the actual bound was. So they bounded the sort of exponential growth rate of this by 1 plus sine theta over 2 sine theta log 1 plus sine theta over 2 sine theta. Is it plus or minus? Minus. Minus 1 minus sine theta over 2 sine theta log 1 minus sine theta over 2 sine theta. So I'm not going to discuss how they got this inequality. It's a nice trick involving the Christoffel-Darboux formula from orthogonal polynomials, but well, let's take this as a given for the moment. So then what they did was they plugged this into here. They chose the value of theta to optimize it, and a very weird thing happened. That the optimal value of theta as n goes to infinity came out to something like 63 degrees. And I find this really bothersome because if it were going to 0, I would say, okay, that's great. We all know that Euclidean stuff is basically the sort of 0 distance scale limit of spherical geometry. And it would be very natural, and I would say, okay, you know, it's a bit weird to do a detour through spherical codes, but it fits. On the other hand, going to 63 degrees, at least in my view, really doesn't fit conceptually. And it's bothered me ever since I learned about it that somehow the best density bounds we know amount to packing, 63 degree spherical codes, getting the best density bound there, and then translating. Not that I'm aware of. I mean, in both cases, these sort of non-constructive arguments, you can carry them out in spherical geometry too. So you can prove lower bounds that are similar in both cases, but I don't know of a direct construction going between them.
Yeah, so the best lower bounds I have mentioned, which are explicit, do use
Mm-hmm. Yep. But they go sort of back to sort of error correcting codes even further than that. Yep. Okay. So
are there good conjectures about these spherical codes?
there are in a lot of concrete cases, but as far as asymptotics go, it's the same situation as sphere packings, that we've got these sorts of upper bounds, there are corresponding non-constructive lower bounds, and they totally don't match.
So it's similar.
Yeah, so it's similar, so it's sort of qualitatively similar, let's say.
Even for fixed theta at large.
Exactly, yep. So basically, theta going to 0 reduces to the Euclidean case. If theta is very large, 90 degrees or so, then it's not hard to analyze. But for any fixed theta strictly between 0 and 90 degrees, it's a mystery. Okay. So let me say a bit about how you would improve this. So I mentioned that we could give a slight improvement. What we can actually show, I should say this is all joint work with Yufei Zhao, who's a grad student at MIT. So what we can actually show is that the Euclidean density bound is bounded by the sine of theta over 2 to the nth times a of n theta rather than n plus 1. Let's assume that theta is between pi over 3 and pi, but for example, 63 degrees satisfies that. So in high dimensions, the spherical code sizes are growing exponentially. This lowers you by 1 dimension. You've got a constant factor. It's practically the same bound, but it's a little bit different conceptually. And I'll say a little bit more later in the talk about why these differences matter. But first of all, let me prove this bound. So how do we prove this? So let's imagine that we've got a packing with unit balls, and it's got density equal to the maximum possible density. So what we're going to do is we're going to pick some radius capital R that's less than or equal to 2. And what we're going to do is look at a ball of radius R. This picture is not to scale. That's terribly not to scale. So what we're going to do is we're going to place this ball of radius capital R on the sphere packing in such a way that it captures at least the expected number of sphere centers. So in particular, a sort of scaling argument shows, let me just call this delta for the moment. A scaling argument shows that an averaging argument rather, shows that there exists a ball of radius R such that it contains delta times R to the n centers of the spheres. So then what we do is we take these sphere centers and radially project them all out onto the surface of the sphere. Let's assume none of them is actually at the center of the sphere. The averaging argument shows, in fact, you can get this many sphere centers that aren't exactly your center. So what we do is we take this ball of radius R, move it around till it covers as many sphere centers as possible, at least the average number certainly. We radially project them all out onto the sphere, and what happens is if we define theta by the sine of theta over 2 equals 1 over R, then this is going to be a spherical code of a spherical code of angle theta. I'll state a more precise lemma about this in just a second. But what this implies is delta R to the n had better be at most a of n theta. And using the relationship between theta and R, we get an upper bound for the packing density. So basically, all we need to know here is that if you radially project outwards, you do get a good spherical code. And this is an easy exercise in elementary geometry. What it amounts to saying is, take 2 of these sphere centers. Let's call them x and y. And let's say that the center here is z. So we have 2 points that are at least 2 units apart. And if we look at spheres of radius r at these points, we've got z, which is in the intersection of these 2 spheres. And what we're doing is we're looking at this angle here. And the claim is that this angle is at most that, theta. And this is pretty easy to see by drawing a picture. If you look at the locus of things where you get exactly that angle, it'll look like this, and it will contain this whole region. It's also, if you just write down the law of cosines or something, it's a 1 or 2 line proof. But the net effect is, if this distance is at least 2, these distances are at most r, then you have a bound for the angle. So any questions about anything so far? Okay. So what have we seen so far? We've seen a simple way to reduce Euclidean sphere packing problems to spherical code problems. What we haven't seen is how to actually get bounds for any of these things. So the fundamental technique here is what are called linear programming bounds. Incidentally, before I erase the hyperbolic stuff, when I said earlier this depended on a little bit of trigonometry, it's this lemma here. The thing is that any geometry where you can prove something like this, you can carry out this argument. Otherwise, you're stuck. So the fundamental technique here is what are going to be called linear programming bounds. And this goes back to Delsarte. And these are more or less the best bounds that are known for any sort of coding theory or packing problem. It's not quite true. There are semi-definite programming bounds that refine these in certain cases. You can think of that as sort of an elaboration of the same basic idea, though. So let's look at how these work in the case of the sphere. So we need the notion of a positive definite kernel. So let's imagine we have a function on the interval from -1 to 1. We're going to think of this as basically cosines of angles. So a positive definite kernel, we'll say that this function is positive definite if for any number of points and any choice of that many points in the sphere, if you look at a matrix whose ij entry is G applied to the inner product between these points, that this should be a positive semi-definite matrix. So an equivalent way of looking at this is if you take this matrix and take the norm of any vector with respect to it. This is equivalent to saying for all xi's in the sphere and for all, say, real parameters ti, that the sum of ti, tj, g of the inner product xi, xj is greater than or equal to 0. So this is a concept that basically arose in representation theory, that understanding which functions are positive definite plays a big role in understanding which representations are unitary. But we're going to be using it for some discrete geometry purposes here. So in fact, an important thing to know if you ever want to apply this is that you can explicitly characterize all the positive definite functions. For our purposes, we're just going to treat them as a black box. But in fact, you've got some cone of positive definite functions. Schoenberg found all the extreme rays in the cone. So there's a theorem of Schoenberg from the 1940s, I believe, which says that a function, let's say a continuous function, is positive definite if and only if it's a positive linear combination of Gegenbauer polynomials with parameter n minus 3 over 2. So what these are is here C. Yes, exactly. So one way of thinking about these is the Gegenbauer polynomials are zonal spherical harmonics, and the spherical harmonics are representations of the orthogonal group. So representation theory is definitely right below the surface here. What these are they're orthogonal polynomials with respect to this measure on the interval from -1 to 1. And this measure is exactly the surface measure projected from the surface of the sphere to an axis. If you take your sphere, you take some axis going through it, you take the surface measure on the sphere, and you just orthogonally project that down onto your one-dimensional axis, you get this measure up to scaling.
Are you going to use linear programming to get the bound up there?
Exactly, yep. So basically, we're going to find a linear optimization problem that will give bounds, and then if you want to optimize it, it's a linear programming problem to do so. But so far, there's been no linear programming on the board. Okay. So let me do one more definition. Let's define the average value, G bar, to be just the average with respect to this measure. So one way of thinking about this is we can take the expected value. If you pick two independent random points from the unit sphere and apply G to the inner product between them, and that you can calculate as exactly this. So you should think of this as sort of the average value of G between two randomly selected points. So here's the theorem that makes linear programming bounds work. It's due to Delsart, Gödels, and Seidel in this particular setting. So what it says is if you have a positive definite function that satisfies certain sign conditions, you get a packing bound. In particular, if G is positive definite, if G is less than or equal to 0 on the interval from -1 to cosine theta. So in other words, G is less than or equal to 0 whenever you have 2 points that are more than theta apart. Then this implies, well, let's also add G bar is strictly greater than 0. Then this implies that the size of a spherical code, I guess I should say for Sn minus 1 to make the n dependence clear. The size of a spherical code, then, is bounded by G of 1 over G bar. So what this says is you want a function that's positive definite. It's got a lot of positive sums. It should be negative whenever things are far enough apart. Whenever you have such a function, this ratio gives you some bound for spherical codes. You can then plug that bound into this lemma and get a bound for Euclidean packing density. Any questions about anything so far? Exactly. So why is this linear? So the quotient's not linear, but without loss of generality, you can scale so G bar is 1. And then what you're doing is you've got a function. You've got a bunch of linear constraints on it. It's in some cone of positive definite kernels. It satisfies a bunch of linear, that's linear. It satisfies a bunch of linear constraints on its values. You're trying to optimize G of 1, which is a linear functional of G. So you've got a linear optimization problem. So the good news about this is computers are very good at solving linear optimization problems. The bad news is that doesn't mean humans can understand them conceptually. And in practice, we don't know the best way to make use of this. In particular, in any given case of theta and n, with just a handful of exceptions, we don't know the best choice of g. There are, yes. So you've got a continuum of constraints here, for example. So I should say it's an infinite dimensional linear programming problem. You can phrase it as a finite dimensional convex programming problem, and it's tractable in a computer. But part of what makes it subtle is really it's infinite dimensional. So the bound. Oh, so you can make it finite dimensional in one sense by choosing a finite basis for g, picking polynomials up to a certain degree. Even still, you've got infinitely many constraints of this form, but you can turn that into finitely many semi-definite constraints, or you can approximate it with a dense subset, or all sorts of things. I mean, in practice, yes, although I don't know in theory. Yep. Other questions?
Suppose I were to find
Yep.
the optimal t
Yep.
smallest one. How close do you expect that to be?
No idea. The thing is, all we know is that it's at least as good as Kapitiansky-Levenstein, but beyond that, it's really not clear. So let me give you a proof of this. What's most erasure worthy? Probably this. By the way, how far down can I write before people have trouble seeing? Okay. So let's prove this. Since, so far, I guess I sort of sketched a proof of that lemma, but this is a nice argument. So this is Kapitiansky and Levenstein's, it's a version of Kapitiansky and Levenstein's argument for this result. So what they say is this. Let's suppose you've got a spherical code C in Sn minus 1, and let's suppose you've got minimal angle at least theta. So how are we going to get a bound from it? So what we're going to do is we're going to look at the following measure. So let's define a measure nu, which is going to be given by a sum over all the points of the code of a delta function at that point, plus some constant lambda, which we're going to determine later, times, let's call it mu, which is going to be the surface measure on our sphere. So we're summing up, so we're looking at sort of delta functions at all the code points plus some sort of background measure with some weight lambda. In fact, lambda is going to be negative. This is going to be a signed measure. So what do we know about this? So it's pretty easy to prove that if we look at G of an inner product and integrate this d nu of x, d nu of y, this is going to be greater than or equal to 0. So it's basically the continuous version of what's set up here. This is for discrete sums. If you have more and more points, you can turn your sum into a measure, and you get that. So this holds no matter what value we choose for the constant lambda. We're going to work out what this means, and then we're going to make the optimal choice of lambda. So what happens if we expand this out? So we have the delta function terms. We have a sum over x and y in the code of g of xy. We have the mu terms, where what we get is, let's take the surface measure normalized to have total volume 1. So we have the mu terms, where now we're averaging two random points, g of the inner product between them. So we get lambda squared g bar. And then we have the cross terms. So we get two cross terms. We're summing over the points in C, and the measure mu is invariant, so we get 2 times the size of C times lambda times g bar also. So what we conclude is that this is greater than or equal to 0. So now we can do one other simplification of this inequality. We know that by hypothesis, G is non-positive whenever our points get far enough apart, and all the distinct points in the code are far enough apart. So we can give an upper bound here of the size of the code times G of 1. And the thing is, if we substitute this in for that, it's still greater than or equal to 0, because all the off-diagonal terms just make it smaller. So what does this tell us? It tells us size of C, G of 1, plus lambda squared plus 2 size of C lambda G bar is greater than or equal to 0. And this holds for all lambda. So we've got some quadratic in lambda. We choose lambda to be the minimum of the quadratic to try to get the most information we can out of this inequality. The minimum happens to be at lambda equals minus the size of the code. And if we plug that in here, it implies the size of the code is at most G of 1 over G bar as desired. So any questions about anything so far? Okay. So now we've seen how to use this positive definite property together with the non-positivity of the values far away from the diagonal to prove bounds in the code size. I've told you that Kapitiansky and Levenstein had a trick for choosing a good value of G. Almost certainly not the best, but it gives a good bound. We can plug that into the lemma in order to get a Euclidean sphere packing bound. And so everything works. Modulo how you choose G, it's a more or less complete proof. What's frustrating about this is it all goes through spheres. And it seems very weird to have this digression through spheres to prove something that's fundamentally about Euclidean space in the first place. You're talking about relaxing this constraint? Okay, less than or equal to a minus epsilon or something? Yeah, so you can try modifying the constraints in various ways. In practice, they don't really seem to help you.
I guess Tom asked this question.
Yep.
Vlada mentions if you run a linear program for fun, that you do better than their choice.
Yes. So their choice, at least in small cases, really doesn't seem to be optimal. The tricky thing is just how you guarantee these properties. So basically, they found a sort of restrictive class of polynomials for which it's pretty easy to guarantee this. Then they optimized the parameters within that family. But there's really no reason to think that it's anywhere near the real optimum. Okay. So what we can do is, Noah Melkes and I formulated a Euclidean version of sphere packing, of linear programming bounds. Exactly. I mean, I don't really think, I think if you knew the true value of A of n theta and you plugged it in, it would feel very weird to me if the best way to use this inequality was really to pick 63 degrees. I think you're right that this is an artifact of the proof techniques, but still, it's the best we know how to do currently. So Noah Melkes and I found a version of LP bounds. I guess LP means different things to analysts and computer scientists, of linear programming bounds that works directly in Euclidean space. So one way of stating it is, let's suppose you've got a function from Rn to R that's going to be positive definite. So what does that mean? It's exactly the same thing as what I erased, only here we look at f of the difference between 2 points. And this should always be a positive semi-definite matrix. By Bachner's theorem, this is the same as having a non-negative Fourier transform. So just to be precise, let's assume f is continuous and integrable. Let's assume it's positive definite. And the f of x is less than or equal to 0 whenever x is at least 2. So you're less than or equal to 0 whenever you're far enough apart. So then what this implies is that the density in Rn is bounded by the volume of a ball of radius 1 in Rn times f of 0 divided by, well, f hat of 0, in other words, just the integral of f. So this is thoroughly analogous to the other theorem. The integral is playing the role of g bar. Everything is analogous. So our original proof of this used Poisson summation. In fact, if you want to prove this with minimal hypotheses without worrying about growth conditions on f or f hat or anything, another way to do it is to imitate this argument, to sort of finitize everything and say, let's take a big ball and let's do a sum like this over all the points in the ball, putting in some multiple of the uniform measure over this ball. Let's optimize that, let the size of the ball go to infinity, you get this bound out of it. So I realize we've got just like 2 minutes left. So the short version of this is, this leads to exactly the same difficulty we had up there. We didn't know how to find g. We don't know how to find f either. And in certain dimensions, I really think there are wonderful auxiliary functions f you could use. So for example, in 8 and 24 dimensions, I believe you can solve the sphere packing problem outright if you choose the right f. We can solve it to 50 decimal places. That's not a proof, but it's very close. In any case, I'd be happy to talk with anybody about ideas for doing this because it really ought to be doable. But what happened is, previously we did not know how to choose f even to recover the Kapitiansky-Levenstein bound. So another thing that Yufei and I do in this paper is we give a general transformation which takes a function g satisfying these hypotheses and turns it into f in such a way that the density bound sine of theta over 2 to the n times g of 1 over g bar is exactly equal to this. So what we show is anything you can do by passing to spheres and then doing linear programming bounds there, you can do directly in Euclidean space. I don't have time to tell you what the actual reduction is. You can write down a pretty simple integral to define f in terms of g. So part of what's, yes? Exactly. Yes. So previously we had gotten exponential bounds not quite as good as Kapitiansky-Levenstein through basically Bessel functions, yeah. And this matches Kapitiansky-Levenstein. It matches the tiny improvement we found. It can't possibly be the right thing to do. The problem is you're taking a sort of complicated ad hoc polynomial. You're taking this polynomial, you're passing it through some sort of funny transformation. You get a function on Euclidean space which is really weird looking. I don't think this is globally optimal. I don't even think it's locally optimal. And I think there ought to be a nearby local optimum that would do, in fact, better. I've got some ideas for how to do this by calculus of variations argument, but haven't been able to make them work. But I'd be happy to chat more about this with anybody who's interested. In the meantime, we're about out of time, so any final questions? Mm-hmm. I doubt it. The thing is, I really think that going through spheres isn't the right thing to do. The transformation is weird enough that I can't prove anything, but I'd be very surprised if the best possible choice of G actually led to the best possible F. I think the right thing to do is to do everything in Euclidean space from the beginning, but this could just be prejudice on my part. Oh, so I should say, yeah, in low dimensions, definitely, if you take, 2 dimensions, this bound is terrible. I forget what the actual answer you get out of it is, but I'm not even sure it's less than 1. So basically, I mean, yep. 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 Mm-hmm. Yep. I believe so, yep.
But it's only in special dimensions.
Yep, only in 1, 2, 8, and 24. That basically, it's not that this bound is particularly good in these dimensions. The bound behaves pretty smoothly in all dimensions. The packings are really jagged, and there are a couple of dimensions where they sort of jump up to meet the bound. And that's not a coincidence. It's connected to a lot of other things, the solution of the kissing problem, optimality of Golay codes, various things. But that's another story. Other questions? About lattice packings? It's funny, the thing is, so the best lower bounds we know all use lattices. The best upper bounds we know work for all packings. There are ways you could try to improve this for lattices. So Nathan Kaplan and I have a sort of souped up version of these bounds that only works for lattices. However, we haven't been able to get any good asymptotics out of it. So right now, the best bounds we know asymptotically for lattices are exactly the same as for non-lattices. Oh, so in dimension 24, using special properties of lattices, we could get close enough to prove the Leech lattice was actually the unique optimum. Among lattices. But in sphere packings, we still don't know it. Excuse me? Yeah, I mean, I'm sure that the sort of optimal functions exist. You can compute them to high precision, you can plot them, you can look at Taylor coefficients, you can do whatever you want to them except prove anything. Of course, that's the big deal. The thing is, proving stuff is the hard part, but at least I'm confident of what's true, even though I've got no idea how to actually do the hard part.
If I fix a dimension like 15,
Yep.
Is there an algorithm, a computer algorithm, which will give you upper and lower bounds, which convert them in a reasonable sense?
Nope. So you can optimize these bounds by computer, and they'll converge to something, but they won't converge to anything sharp. You can try searching for a packing, and eventually you'll get stuck and be unable to improve something, but there'll be a big gap between them. And yeah, so in 8 and 24 dimensions, we can come arbitrarily close, it seems. On the other hand, in every other dimension above 3, there's just a fundamental gap in our knowledge, and even improving the bounds by 10% would take some work.
So there isn't even an algorithm that would do the job, or is that?
So for lattices, it's algorithmically solvable, but undoable above 8 dimensions. For non-lattices, it's not even clear a priori how complicated the answer could be. The thing is, if you look at like a periodic packing with a sort of a fixed number of translates of a lattice, that you can optimize in principle algorithmically, but we have no a priori bound for how many translates you need.
Even Hale's work
Yep.
algorithmically, his work does not stop and say, this is an algorithm that does a finite calculation, provides a proof. Only when the algorithm runs does it take shortcuts. Only when it's finished does it verify that.
Exactly. So really, we've got no idea how to treat things like this algorithmically.